All right, so we're going to take a look at our last section, okay, which is 4.2. As I said, we'll split that into 2 days. It's graphing. Okay, that's what most all of this section is. But we're going to look at 2 different kind of cases we can have. We're going to look at the first case today, and then the second case tomorrow. Okay, so when we are graphing, we've learned that there are a couple different kinds of things that can happen when you divide by 0. Okay, one thing that can happen when you divide by 0 is you get a graph that looks like this. 1 divided by, let's do x minus 3. Okay, so when we do that graph, when we get to positive 3, we get something right here, this vertical thing. Does anybody remember what we call that?
Vertical asymptote.
Yep, that's a vertical asymptote. So a vertical asymptote is caused, can be caused, when you divide by 0. Right? And it's very easy to see on the graph. Now, let's look at this. Let's do x squared plus 4x plus 3. And let's divide that by x plus 1. Is there a number there that would cause you to divide by 0? Yeah, what value for x would cause that to happen? -1. So let's graph it, and let's see what happens at -1. So we're dividing by 0 like we were in the last one, but this time you can't tell anything, right? There's no vertical asymptote in this graph. You can go to the table, and you can confirm if you type in -1, it is an error, right? It's undefined, you can't do it. But you don't get that vertical asymptote where the graph curves up and down very steep. Right? And that's because in the second one, I had a common factor. Okay? If it didn't look like I had a common factor, it's just because of the way I wrote it. Look at that. The numerator was x squared plus 4x plus 3. But if you factor it, watch what happens. It becomes x plus 1, x plus 3. That's the numerator factored. And in the bottom, you had an x plus 1. What happened there is you have a common factor. Common factor of x plus 1 in the top and the bottom. When you have a common factor, you can get a break in the graph, a discontinuity, that you don't notice. So if we were going to graph something like this, and you really wanted to show what it looks like at -1, you should put an open circle on the graph right there. Okay. That -1 shows that you have a hole in the graph. Okay. And you wouldn't even draw the line through it. You just do it just like that. Okay? So we always have to make sure we look for those, and the only way to find them is to factor it and look at it. You cannot tell that there's a hole in this graph by looking at a picture. All right. What would happen if we don't have to graph this one, but what would happen if I did? All right. To figure that out, first thing you ask yourself is there a value that would cause you to divide by 0? Let's start with that. So what do we think? Is there a value that would cause you to divide by 0, right? Yeah, 1. Okay, if you plug in 1, that is going to cause you to divide by 0. So now, it's not a question of if we're going to divide by 0, we are. If you plug in 1, what happens when you divide by 0? Do you get a hole, or do you get a vertical asymptote? Do we have a common factor in the top and in the bottom? Yeah, yeah. Yeah, we do. We've got a common factor. So when we have a common factor, do we get a hole in the graph, or do we get an asymptote in the graph? That's going to be a hole. Yep. So there would be a hole in graph when x equals 1. Okay, that would be a hole. All right. Any questions on that one? Okay. How about this one? X minus 1 squared over x minus 1. Is there a value you could plug in for x that would cause you to divide by 0? Yep, what would that value be? 1. And would you have a hole in the graph or vertical asymptote? You'd have a hole again. Okay? If you write this out, it's 2 copies of x minus 1. So you do have a common factor in the top and the bottom. And that results in a hole. So same thing in this one. Hole in the graph when x equals 1. Okay. What if I had, let's do one more, h of x. Okay. Is there a value there that I could plug in for x that would cause me to divide by 0? Yep, what would it be? 5. Do we have a common factor in the top and in the bottom this time? No. To have a common factor, you need another x minus 5 in the top. So at 5, are you going to have a vertical asymptote or a hole in this graph? Yep. So this will have a vertical asymptote when x equals 5. Questions on that? Okay. And you could have some graphs that have both. Okay. Here's an example that has a hole and an asymptote. Let's do okay. What are the two numbers that I could plug into the bottom that would cause me to divide by 0? 3 and 4. Now let's start with the 3. When x equals 3, is there a common factor of this in the top and in the bottom? Yeah. Yes, there is. So what's going to happen when x equals 3 on the graph? There's going to be a hole. Okay. And now the other one you said is when x equals 4. Okay. When x equals 4, is there a common factor of x minus 4 in the top and in the bottom? Well, there isn't. So when x equals 4, what's going to happen? There's going to be a vertical asymptote. Okay, so sometimes a graph has a hole, sometimes it has an asymptote, sometimes it has both. This one has both. Okay, so any questions on that? All right, so, well, I don't want to say in example 1 there was no vertical asymptotes because I did do some that were, some had holes, some didn't. So let me just rewrite that. In example 1, when there is no vertical asymptote, so when there was no vertical asymptote, we have what's called a removable discontinuity. Okay, a removable discontinuity, that's the fancy word for a hole in the graph. Okay, it's infinitely small, but it's there. So in example 1, when there was no vertical asymptote, we have a removable discontinuity. It just means it's a hole in the graph. All right, so we're going to be looking at problems like this. And what we're going to have to do is describe what it looks like, kind of like big picture. So I talked a little bit about this yesterday, EBM. Does anybody remember what that stood for?
End behavior model.
Right, end behavior model. And the end behavior model was always the term that had the highest degree. Okay, so I'm going to rewrite this. So let's write that down. So, from yesterday, the EBM of a polynomial is the term with the highest degree. So if I had something like, let's say, 8x cubed minus 5x to the fourth plus 3x minus 7, what term there is going to control what the polynomial looks like? Which one? So we have four terms there. Your choices are 8x cubed, negative 5x to the fourth, 3x, or negative 7. Which one? Yes, negative 5x to the fourth power. That entire term is what's going to control what it looks like, right? So that's with just a single polynomial. Now I want to look at what happens when we have a rational function. For a rational function, you're actually going to have to find two EBMs. So for a rational function, the EBM is the EBM of the top divided by the EBM of the bottom. That's the EBM of the entire thing. So the EBM is the EBM of the top divided by the EBM of the bottom. It's not really that much harder to find the EBM for the rational function. Okay? You just have to find two EBMs and divide them. So say, for example, you had 8x squared minus 3x plus 2 over 4x plus 7. And I said to you, find the EBM of that. Start with the EBM at the top. What's the end behavior model for the top? 8x squared. And remember, what that EBM really means is that 8x squared gives you an idea of what this is going to look like if you zoom out. It's not an exact copy of it, but it's a general idea, okay, of what this would look like without all the little details. So 8x squared predicts what the top is going to look like. And what term predicts what the bottom is going to look like? 4x. Now, when you write an EBM, you do have to reduce it as much as you can. 8 divided by 4 gives me how much? So that gives me 2. And what's x squared divided by x? X. That's the EBM for that problem. Okay, and let me graph that so you can see what it looks like. Okay, so we've got 8x squared minus 3x plus 2. And we're going to divide by 4x plus 7. I might have to zoom out a little bit. Yeah, let me go further to the left and let me go further down. See if you can see the other piece. There it is. So there's a piece in the lower left, and then there's a piece in the upper right. I'm going to go even higher to the right so you can see that one better too. Let's go like this. So that's the original problem. Now I'm going to graph the EBM, and I want you to see what it looks like. Remember, the EBM is not going to show you what's happening in the middle. It's going to model what's happening on the ends of the function. Okay, so if you look at that, don't look at what's happening in the middle. Okay, pretend like you can't even see that part. Okay, so don't want a circle. I want this. But I want to fill it in. Okay, so don't look at the middle. Just look at the ends. Do those two functions look pretty similar? That's what the EBM is designed to show you. It's a much more simple version of what you started with, but it still basically predicts what it's going to look like over here and what it's going to look like over there on the ends. Okay, the middle, no, it's not even close to what it looks like in the middle. But that's not what the EBM is for. It predicts what happens on the ends. Okay. So why don't you guys try that one? Take a minute, see if you can find the EBM. Actually, put up a couple of them. And then once we find the don't worry about the horizontal asymptote yet. We're going to do that together. I just want you to see if you can find the EBM for each of those. What do we get for the EBM for the top in part A?
I had 2x squared.
2x squared. Perfect.
Over 3x squared cubed.
3x cubed. Okay, and in this case, 2/3 isn't going to reduce. So we're going to just leave it as 2/3. And we had x squared over x cubed. So first thing to figure out is when we're done, where are the x's going to be left? Are we going to be left with x's in the top or x's in the bottom? Where? Bottom, yeah. Because if it's tricky, think of it as x times x in the top. Think of it as x times x times x in the bottom. There's 3 of them. 2 in the top are going to cancel. 2 in the bottom are going to cancel. And we're left with just 1x in the bottom. So the way you're going to do that is 2 over 3x, and that's your EBM. Okay, let's do the bottom one. What do we get for the EBM in the top? 2x to the 4th over 3x to the 4th. Again, 2 over 3, that's not going to reduce. But what's going to happen with my x to the 4th in the top and the x to the 4th in the bottom? They're going to cancel out completely. So this time, the EBM is just a number without a variable. That can happen. So sometimes the EBM has a variable in it, sometimes it doesn't. Okay. Now, the next part they said is find the horizontal asymptote. So let me explain how you do that. Okay, so to find the horizontal asymptote, first thing you're going to do is you need the EBM. Okay, so that's why we did that first. Use the EBM and let x approach infinity. Okay, so as we let x approach infinity, this gets really, really big. And 2 divided by something really, really big gets really, really small. And it's approaching what number? It's approaching 0, yes. So in this particular problem, the horizontal asymptote is That's fine. Yeah. The horizontal asymptote is y equals 0. So we look at what happens to the EBM as x approaches infinity. There's only going to be two options for the EBM today. It's either going to approach 0 or it's going to approach a number. Okay? This is the example where it approaches 0, and that occurs because there's a variable in the bottom of the fraction. Let's look at this one. Where's the x in this EBM? There is no x. Okay? So let's try to do the same thing again. Use the EBM. I want you to look at that fraction. Let x approach infinity in that fraction. But there is no x. So what happens to this fraction as x gets bigger and bigger? Nothing. So what does it stay as? It stays as 2/3. So your horizontal asymptote here is 2/3. So when all the x's cancel out, the EBM is just going to be a number, basically, of whatever the coefficients were in front of the x's. If all the x's don't cancel out, and you're left with an x in the bottom, then the EBM is telling you that the horizontal asymptote is always at 0. Okay? If it's left in the top, that's part 2. So that's tomorrow. That's not today. So for today, the x will either be left in the bottom or it won't be left at all. Okay. Yes?
What if there's no x's or numbers left?
Well, you'll always have something left. You'll never end up with nothing left. Because even if these were the same number in the top and the bottom, like 2 divided by 2, you're not left with nothing. You're still left with 1. Okay, so those are the kind of problems that we're going to look at and we're going to try to sketch right now, where the degree in the top is always less than or equal to the degree in the bottom. And those are what you just looked at. In this first problem, the degree in the top was a 2, degree in the bottom is a 3, the degree in the top was less than what was in the bottom. And then in this one, the degree in the top was a 4, degree in the bottom was a 4, and they were equal. Can it be bigger? Yes. You can have the degree in the numerator greater. That's tomorrow. Okay, so these graphs have generally several pieces to them. Okay, they're not one connected piece. So that means we need to kind of put a little bit of thought into how we sketch it. Something that can help us to sketch the graph is finding the intercepts, both the x-intercept and the y-intercept. Okay. To find an x-intercept, you plug in 0 for y. Okay. That's how it works. To find the y-intercept, you plug in 0 for x. Now, this sometimes isn't helpful because if you had a graph that looks like this one, well, actually, let's see if we have this one. Yeah, this, no, that one actually isn't good. Let me make up a new graph. Let's graph 1 over x. Finding the intercepts in this graph wouldn't be useful because there are none. This graph never crosses the x-axis and it never crosses the y-axis. So sometimes finding the intercepts is impossible and it won't help. But if it is possible, it can help. Next thing we want to do is find the vertical asymptotes. Remember, the vertical asymptotes are where the denominator is 0, as long as we don't have any common factors. What happens when you have a common factor? Instead of a vertical asymptote, you get a hole in the graph. Okay, so 0 is a denominator as long as there are no common factors. So if you've got the same factor in the top and the bottom, that's a hole. Okay, so we're going to find the vertical asymptotes. Then we're going to find the horizontal asymptotes. Okay, how do we find the horizontal asymptotes? when you get a function that's kind of complicated like this, you find a simpler version of this function. That's called the EDM. So then you look at the simple version, and that will help you to find the horizontal asymptotes. Okay, the EDM is always a much simpler version than the original, but it's going to predict exactly what the function is going to look like on the ends. And that's what you need to be able to predict to do the horizontal asymptote. What does the function look like on the ends? Okay. So after you've done steps 2 and 3, you're going to have kind of like a grid now. Probably going to end up with 2 vertical asymptotes, and you're going to end up with a horizontal asymptote. So now you're going to have different sections you have to draw in. You'll never have, this would have 6 sections. You won't be drawing in all 6. You'll generally end up drawing 3 pieces. That's what this graph is we're going to do is going to look like. So I'll have three parts to it. Okay. So we learned yesterday, as you get close to a vertical asymptote, one of 2 things always happens. The vertical asymptote in this problem is at 0. As you approach 0, you either start heading up forever or down forever. We have to see which one it is. So we're going to check what's happening very close to the asymptote on the left side and very close to the asymptote on the right side. And when we do that, it's going to do one of 2 things. It's either going to head up to infinity or down to negative infinity. You're just going to figure out which side is which. Is it doing this? Or is it doing something like that? Which way is it going? Okay, and then after we have all that information, that should be enough to get a pretty good sketch. We've got to confirm with the graphing calculator what's going on. Okay, so there are a few parts to sketching this. It's not as simple as like sketching a parabola or a straight line, but if you follow those steps, it'll help. Okay. Does everybody have those 5 steps? Okay. So let's sketch a complete graph of that. X minus 1 over x squared minus x minus 6. Now, the first thing I would do is if you have something that's quadratic, try to factor it. Okay, because you're going to need that factor to do some of these 5 steps. Not all of them, but it's definitely helpful for step 2 if you factor that. In the bottom, we've got x squared minus x minus 6. What would be my first term in each set of parentheses? Yep, x and x. And what would be my signs? Both positives, both negatives, or one of each? One of each. Yep. Each. And 2 numbers that multiply to give me 6. But they have to subtract to give me a 1. 3 and 2. And because I want it to be a negative 1, I'm going to put 3 with the negative, and I'll put 2 with the positive. And let's check it. So x squared minus 3x plus 2x. Okay, everything looks good. Okay, so depending on which one of these 5 steps we're trying to do, we're either going to use this version. That'll be easier for some of them. Or we're going to use this version. That'll be easier for other steps. Let's do the intercepts. Let's start with the y-intercept. The y-intercept is when you plug in 0 for x. Okay. So you're basically trying to find the point like 0, comma, and then we're trying to figure out what this number is right here. If we plug in 0 for x, what do you get in the top? Negative 1. And if you plug in 0 for x in the bottom, what do you get? Negative 6. So the y-intercept is 0, comma, 1/6. That's a point on the graph. So that's right about there, just above the origin. All right, so that's good. Now we need the x-intercept. That's when you reverse it. Now plug in a 0 for the y. There's no y up here, but f of x is another name for y. Yeah, that is your y. So now you're basically going to set this fraction equal to 0. So you have something like this. 0 equals, then you have your fraction. What's the only way that a fraction can ever equal 0? If you get 0 in the top. Yep. So what we're doing now is we're trying to figure out this number. Before we were doing that number. If you set this equal to 0, what's the only way you could get 0 in the top here? If x is 1. Yep. So 1, 0 is your x-intercept. Okay, so we got 2 points. Okay, next thing we need are the vertical asymptotes. Those are the zeros of the denominator. For this one, it's going to be easier to look at that version. How many numbers could we plug in that would make the denominator 0? 2. What are the 2 numbers? 3 and -2, and I don't see any common factors in the top and the bottom. They're all different factors. So we are going to have 2 vertical asymptotes, no holes in this graph. Okay, so -2 and +3. All right, let's sketch those. So I've got a vertical asymptote at -2. I got another vertical asymptote at +3. And then that's it. So those are my vertical asymptotes. Okay, next thing I need is my EBM. Okay, EBM is going to be used to get the horizontal asymptotes. Make this easier to see again. Okay, EBM. What is the EBM of the numerator? X. What's the EBM of the denominator? And for this one, it's actually easier to look back at the original problem because you need everything all together to see the highest degree term.
X squared.
X squared. Yep. And if you reduce that, what does x over x squared reduce to? Well, where do we have more x's right now? In the bottom. So when we're done, we still need to have more x's in the bottom of a fraction. 1 over x. Now, that's the simplified version of the original problem. And this predicts what the ends of the graph are going to look like. What the ends of the graph are getting close to, that's the horizontal asymptote. As x gets bigger and bigger, what's going to happen to this entire box? It's going to get smaller and smaller because the denominator is getting bigger and bigger. And it's going to get smaller and get close to what number? 0. Yep. So there is your horizontal asymptote. So let's put that in. So horizontal asymptote is y equals 0. And remember, we had a point right here. I kind of covered it. And the last step we need is to check the behavior near each side of the vertical asymptote. Okay, step 4. All right, so for that, we're going to use the calculator and use the table feature. So type it in. Okay, when you type it in, make sure the numerator is in parentheses and the denominator is in parentheses. go to the table. And remember the two numbers we're not allowed to type in? Let's check them. When I put in -2, what should it tell me? Error, because I'm trying to divide by 0. Can't do that. And when I put in 3, it tells me the same thing. But what I really want to check is the behavior near those numbers. I already know what happens at those numbers. It's undefined. So let's start with -2. Let's pick a number that's just a little bit to the left of -2, like over in this area right here. What would be a number that's just a little bit smaller than -2? When I say a little bit, I want to be within like 100th or 1,000th. Yeah, that's good. -2.0001. Right? Very, very close to -2. So it's not going to give me an error because it's not -2. But I get -6,000. So what that tells me is when I'm to the left of -2, I am way down there. Now, let's check what happens to the right of -2. What would be a number that's just a little bit bigger than -2? Yep, -1.999. And when I plug that in, I'm up at +6,000. So that's what usually happens. One side is very low, other side is very high. Okay, so we got that point. And now let's check what happens near 3. One side is going to be low, other side is going to be high. Okay. What's a number that's a little bit to the left of 3? Yep, 2.99. Okay, and we're down at -400, so we're going way down here. And just to the right of 3 would be like 3.001. We're up at 4,000, so we're up very high. Okay, so as far as the middle, I've got a pretty good idea of what's happening in the middle section. I can see 4 points. They all have to be connected in the middle section, but I have to stay as close to the vertical asymptotes for as long as I can. All right, so I'm going to try to stay really close to this. But I have to start curving away because I have to go through these 2 points. But I can't keep going to the right because I run into another vertical asymptote, which causes me to bend down and go right through that other point. So that's pretty much what the middle looks like. Now I have 2 other sections, one in the upper right, one in the lower left. The one in the upper right, I don't know what that looks like, so I need another point. I would say 1, 2, 3, 4, maybe 5. Let's plug in 5 for x, just get another point. 5, and then we're at about 0.3. So 1, 2, 3, 4, 5. We're at about 0.3. Okay, so I need to connect these 2 dots, but I can never cross the vertical asymptote. Okay, that's important to remember. You can cross horizontal. You never cross a vertical asymptote when you're sketching. Never. So I'm going to try to stay close to it. But I have to start to curving away from that. So I'm going to go through here. But I can't keep going down because then I'm going to start to level off on the ends of the function like this. So that's what that section in the upper right looks like. And then in the lower left, it's kind of the same thing as the upper right. I only have 1 point. So let's get another one. I'm going to do -4. It doesn't have to be -4. It just needs to be in there somewhere so I can get an idea of the curve. -4, negative, we'll call it 0.4. 1, 2, 3, 4. Maybe about right there. So -4 and then down almost a half. And now we have to connect those dots. So we have to stay close to that. As we come up, start to curve, and then get closer and closer to that horizontal, just like that. And that should be a pretty good sketch of that one. So there's your lower left. Looks like the middle should have been a little flatter than I drew it, but that's okay. It's the basic basic idea we're looking for. Okay. So any question on that? All right, we'll try one more of those, and then that'll be it. So this time, the degree in the top was smaller than the bottom. And for the last one, they will be equal. Okay, so again, first thing I always do is factor the denominator. This time, the only kind of factoring you can do is to take out the GCF. What's the GCF between those two terms? What is it? Well, the number, yeah, 2 and 5 have a GCF of 1. But what about 2x squared and minus 5x? Yeah, we can factor out an x. And what, Ruben, what would that leave you with inside the parentheses if you factor out an x?
You get 2x.
Yep.
Minus 5.
Minus what?
5.
Minus 5. Good. All right. So now that should make finding the vertical asymptotes a little easier. What's one number you could plug in for x that would cause the bottom to be 0? What is it? Yep, 0 is definitely one number. You could plug that in right here. And what could you plug in right there? That would make that one 0. Uh, 2.5, yeah, 2.5. Okay, so there's our verticals. For the horizontal, what do we find first that makes the horizontal easier? Yep, find the EBM. Okay. What's the highest degree term in the top? And the highest degree term in the bottom? 2x squared. And if you simplify 3x squared over 2x squared, what do you get? 3 over 2. Now, looking at the EBM, let x approach infinity and tell me what happens to the fraction 3 over 2. It stays the same. So this is going to look just like the other graph. Same curve in the middle and the same two pieces, except your horizontal is going to be up at 3/2, or 1.5. Okay, and for this one, I'm not going to worry about the intercepts. Okay, so let's graph our asymptotes. We've got one at 0 and one at 2.5. So there's 0. There's 2.5 roughly. And the horizontal is 3/2, which is 1.5. So 1.5 right there. Okay, so let's put all that in, and then we'll start checking the behavior on each side of the asymptotes. All right, so we've got 3x squared plus x minus 4, and divide by 2x squared minus 5x. Okay, let's check our two asymptotes and make sure that those numbers are what we thought. What were my vertical asymptotes?
0.
0, good. 2.5, good. Okay, what's a number that's a little smaller than 0? Negative 0.001. Way down. So to the left, we're way down. To the right, we're probably going to be way up. Yep, up at 8,000. Okay, let's check the other vertical. That one's at 2.5. What's the number that's just before 2.5? 2.4. that's pretty close to 2.5, and we're down at almost negative 35,000. Okay, so way down here. And what would be a number that's a little bigger than 2.5? 0, 0, I would do it like that. 2.5001, that's pretty close. And you're up at, again, over 34,000. So way up here. Now, I like to get one more point in each section in the upper right and lower left. So I would do 1, 2, 3, 4, maybe 4 or 5. That's actually a good point, 4, 4. 1, 2, 3, 4. 1, 2, 3, 4. And let's do one that's over in this section. Negative 2 might be a good point. Negative 2, we're at 1/3. Negative 2, up 1/3. Okay, let me make the sketch. So this section is going to curve like that. Middle section, that's going to be pretty steep. I kind of want to get one more point in the middle because I don't know what's happening right here. So let's do 0. Oh, I can't do 0. Let's do 1. Yeah, let's do 1. 1, 0. All right, that's good. All right, so it's very, very steep in the middle. It's going to kind of curve, go through that point, and then down like that. And then in the upper right, it's going to go through these 2 points, curve, and start to get closer and closer. Now, when I graph it, because this one is so steep, I think the calculator is going to have a hard time drawing it. Yeah, it did. That's not quite, it should look like what I drew, not this. This part should keep going down, and that part should keep going up. When it gets too steep, the calculator can't do it. But that's basically what you should have. So that's sketching rational functions, part 1, and then we'll finish the section tomorrow with part 2. So those are the questions for tonight. This is the last homework assignment for the week. So tomorrow night, you'll have the take home, and then that'll be due on Thursday, but I'll put the details in the video tomorrow night. And I will be after school on Wednesday, if anybody needs to check it.